good so far. But now if I take this vertical line with this horizontal line, I get 90 degrees. I don't get 45 degrees. And so that's a different angle. And so therefore, this set of 4 lines in 2 dimensions is not equiangular. Okay, so this is a non-example here. This does not give us 4 equiangular lines. So we can't just simply keep taking polygons with more and more sides. That's not going to work out for us. So somehow we can get 3 equiangular lines this way in dimension 2. We can't get 4 in this way. Okay. Now, if we move up to 3 dimensions, we can consider a similar constructive idea. So here in 3 dimensions, we take a regular icosahedron. So this is a regular icosahedron, lives in 3 dimensions. And then we can join each vertex to its antipode. And this will give us 6 lines. There are 12 vertices on an icosahedron. So we get these 6 lines. Hopefully you can see them here, even though they're slightly on the move. But this is the rotation is just to give you this 3D impression. This is a 3D object, so we're living in 3 dimensions. And here we can get 6 lines. And then you can check yourself, are these equiangular? So one way to do that is just take some embedding of your regular icosahedron centered around the origin, write down the coordinates of its vertices, form the lines, check the inner products, and you'll see that you do indeed get an equiangular line system of 6 lines in 3 dimensions. Okay, so far we've seen how to get 3 equiangular lines in 2 dimensions, 6 equiangular lines in 3 dimensions. And hopefully we have some intuitive idea of equiangular lines themselves. So now we'll look at a more formal definition of an equiangular line system. So it's the same definition, I'm just encoding it using some vectors. So here's the setup. If we let X be a system of n lines spanned by these vectors u1 up to un, and we assume that they're unit vectors. So the inner product of each vector with itself is equal to 1. So we're going to think of lines as spanned by some vectors. So I have n lines, so I need n spanning vectors. And we assume they live in d-dimensional real space. Then notationally, just to give you a bit of notation that we're going to use, I can write X is this set here. So I write these square brackets to mean the line spanned by some vector. So it spans the whole line. So I have these n unit vectors spanning n lines, and that's my set X of equiangular lines. And now the definition of a set of lines being equiangular can be checked by taking the absolute value of the inner product between any pair of these spanning vectors. And so, okay, I see a typo here. Sorry about this. This should be a U, not a V. So some of you are looking at a V and being like, where did the V come from? Well, it should be a U. So this is Ui inner product Uj. The absolute value should be alpha. And alpha is corresponding to the angle, the constant angle that any pair of lines in our equiangular line system induces. So this is not really the angle like 60 degrees, but you can easily transform this by taking inverse cosine. So if you want, you can just say inverse cosine of alpha is the angle we're after, but we don't really care about the units we're using for our angle, so we can just say it should be a constant, and let's take this inner product to be the constant that we're after. Okay, so this is the technical definition of an equiangular line system. And now we can introduce the main problem that we're going to concern ourselves with, and that's this problem here. So the problem is we fix some d. D is for dimension, what dimension we're living in, And we want to know what is the largest possible size of an equiangular line system living in D dimensions. So this is the big problem that we're going to focus on in this session on equiangular lines. And this problem has lots of applications. So in lots of different areas of mathematics, a problem can boil down to finding a bunch of unit vectors where there's constant absolute value. So for example, in fingerprinting codes and other areas of algebraic coding theory, and there's even a recent exciting connection with quantum information theory. So this underlying problem, it looks like a very natural geometrical problem, but it also has very modern applications. Okay, so let's recap what we've done so far. So we've seen how to get 3 equiangular lines in 2 dimensions. And to do that, we use a regular hexagon centered around the origin. And now if we recode that into the definition we just saw here using unit vectors, we can embed the regular hexagon into 2 dimensions, give each point some coordinates, and if we work out the coordinates, we can take the following vectors as our spanning vectors. So we can just take 1, 0 to be a spanning unit vector, and then these other 2 vectors, so we have these 3 vectors spanning our 3 lines. And if you work out the inner product of any 2, the absolute value will be 1/2. So this is something you can check. So let's do one easy example. If I take the inner product of this one, 1, 0, and this one, 1/2 √3/2, inner product will just be 1 times 1/2 plus 0 times √3/2, which is 1/2. Okay, good. So this is one example reformatted into this new way of looking at equiangular lines using spanning vectors. And also in 3 dimensions, we saw we can get 6 equiangular lines from a regular icosahedron. And a way you can do that is quite a nice way, actually, of encoding it, is to take a single vector v. So here's my vector v, where I have phi is the golden ratio. So here's the golden ratio, 1 plus √5/2. I take this vector where I scale it by 1 over square root of phi plus 2, and the entries are golden ratio, plus or minus 1, and 0. So this is 2 different vectors. And now I take all cyclic permutations of that vector. And so that will give me 6 vectors in total. And then I can check the inner product between any pair will be plus or minus 1 over square root 5. So that's a neat way, quite a clean way of generating all the spanning vectors that correspond to 6 equiangular lines in 3 dimensions. So this is, again, just the regular icosahedron, and this one is just the coming from the regular hexagon. So this is what we've seen. Now let me show you some other constructions. So here, this construction at the top is a general construction in any dimension. So here I'm going to show you how you can get D equiangular lines in D-dimensional space. And it's very easy. You simply take an orthonormal basis for your D-dimensional space. So you just take any orthonormal basis you like, and these will be unit vectors, and the inner product between any pair of vectors in your orthonormal basis will give you 0. And so therefore we get that the absolute value of inner product between any pair of vectors is a constant, it's just 0. And so this immediately gives us a lower bound for our main problem. So the main problem is to find this n of d, the largest cardinality of an equiangular line set. And with this general construction, we know that we can always get d, we just start with an orthonormal basis. So this is immediately considered a boring construction. It's like not very interesting. it's somehow obvious we can get an orthonormal basis and get D equiangular lines in dimension D. So from now on, we're only interested in when we can do better than D lines in D dimensions. Okay, and now another nice construction that I'd like to show you is how to get 28 equiangular lines in 7 dimensions. And this also has some nice structure where you take a vector and then you permute the entries. So to get 28 equiangular lines in 7 dimensions, you start off with this vector here. So just say V is this vector 3, 3, and the rest are -1s. And then you normalize it so it's a unit vector. And then you take all permutations of these entries. So you have 3, 3, -1, -1, and so on. And then you might swap this 3 and this 1. So you have -1, 3, 3, -1, -1, and so on. You take all permutations of that, and that will give you 28 different vectors. And then you can check the common angle, the inner product between any pair of these 28 vectors will be ±1/3. Okay, and so that also gives us an equiangular line system. Now, if you look at this vector carefully, you'll think, wait a second, this is in dimension 7, but how many entries do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 coordinates. So shouldn't this be r to the 8? Well, naturally, this fits in 8 dimensions. However, each vector, each permutation of this vector is orthogonal to the all ones vector. So if you add these up, 3 + 3, so imagine you're taking the inner product with the all ones vector. That'll be 3 × 1 + 3 × 1 -3 × 1, and so on. So if you add that up, you'll get 3 + 3, and then -6 ones. And so that will give you 0. So every vector is orthogonal to the all ones vector. And so therefore it fits in a smaller dimension. So they're all orthogonal to the all ones vector. So they fit in not r to the 8, but you can project them into r to the 7. So that's why we see r to the 7 here, even though there's 8 coordinates, because this equiangular line system fits in 1 dimension smaller. Okay, so now I can get to the aim of this course, the aim of what I'm going to talk about today. So I mentioned the big problem, and that's to find this N of D, the largest system of equiangular line systems that fits in R to the D. So what I want you to take away from today is, first of all, understanding of what equiangular lines are. And the second thing is how to find the answer to the question for these small dimensions. So we've made a lot of progress in the last 45 years. So this is what was known in 1976. Here we have a bunch of dimensions, D, 2, 3, 4, and so on, up to dimension 20. And here is N of D, the largest number of equiangular lines we can fit in the given dimension. And there was a lot of unknown. So in this, the blue one gives us the largest construction. So in 1976, the largest construction had size 28, but the upper bound, the best upper bound we knew was 30. So there was a gap here, but this has been answered now. And similarly for 16, there was a gap of 2. It's been answered. 17, another gap of 2. That's now been answered. And here you can see that some of the lower bounds have increased and some of the upper bounds have decreased. So loosely speaking, the aim of this course is to, I want you to know some of the techniques used to get these black numbers. Now, if we look at what we've seen so far, we've seen that we can get 3 equiangular lines in dimension 2 and 6 equiangular lines in dimension 3, but we haven't shown that that's the best possible. So we know that we can construct them, but at this point, it could be possible that there's a larger construction, right? So in order to answer these questions for dimension 2 and 3, we need to have some upper bounds for how well you can do. So that's something to look out for. That's the first thing we'll look into. And we can also see a 28 is here, and that's this 28 lines in dimension 7 is showing up. And that's a very special construction, as we'll hopefully see. So that's what I want you to take away from this. And feel free to ask questions at any point throughout. I'll briefly check the chat box every so often. Okay, so let's do this general upper bound. So I want to show you how we can get a general upper bound, which is occasionally going to coincide with a construction. So this is called the absolute bound. And this says that if X is some equiangular line system consisting of n lines in dimension r to the d, then we get an upper bound for n. So n is at most d times d plus 1 divided by 2. So this is the first thing I want us to understand. And so I want to show you a nice proof of this result. And the idea of this proof is to use polynomials. And throughout this talk, I want to give you the idea that using polynomials is a good idea. So if I go back to this table, in the 1970s, they made a lot of progress using linear algebra to improve these bounds. And sporadically, it was shown that if you move away from matrices, away from linear algebra to polynomials, and let polynomials be the objects that you're working with, you can improve what is known a bit. And so later today, I want to emphasize this idea that modeling the problem using polynomials leads to stronger results. So this is a small example here using the polynomial method. So this is what we're going to prove, this upper bound. Okay, so how does it work? Well, first we let alpha be the angle for this equiangular line system. This is the common angle. And we're going to use u1 up to un to be our spanning vectors for our equiangular lines here. Okay, so that's step one. We take some unit vector for each of our n lines. And now for each spanning vector, we're going to define a particular polynomial. So for each of these ui's, we define this polynomial f sub I like this. So it's the inner product of the unit vector with some vector consisting of d variables, and square that minus alpha squared times the inner product of x with itself. So this vector x is just a vector of indeterminates, just a bunch of variables. So we have d variables, x1 to xd. Remember that each of these spanning vectors ui lives in r to the d. So they have d coordinates. You take the inner product with this vector x that has d coordinates, d variables, and you square that thing, and then you minus alpha squared times, and then this inner product here is just x1 squared plus x2 squared all the way up to xd squared. And so the first thing to observe here is that this polynomial consists of monomials that have degree 2. So we say it's a degree 2 homogeneous polynomial. So every monomial in this polynomial has degree 2. So it's some constant times xi times xj. So hopefully you can see that, because here we'll have the entries of ui multiplied by these things, x1 up to xd, but then we square it. And here we have x x1 squared plus x2 squared, and so on. So each of these polynomials, all the monomials have degree 2, so we call it a degree 2 homogeneous polynomial, and it has d variables in total. The variables are just x1 up to xd. So it's a multivariate polynomial with d variables. And so because of that, we can use the fact that these polynomials, homogeneous degree 2 polynomials with d variables, forms a vector space. So you can think of, instead of these polynomials, you can map them to vectors, and they live in a particular vector space that has dimension d times d plus 1 over 2. And this is the upper bound that we're after. So the polynomials live in this vector space of dimension d times d plus 1 over 2. And so in order to get this upper bound, we can just show that the polynomials we defined are linearly independent. So if they're linearly independent and they live in a vector space of a particular dimension, then the number of basis elements, the size of a linear independent set is bounded above by the dimension of the vector space. And so that will give us an upper bound on the number of polynomials possible, which corresponds to an upper bound on the number of lines possible, since each line corresponds to a polynomial. So that's the main idea. So we define these polynomials and we observe that they live in this vector space with the dimension that we want. And so all we need to do is show that these polynomials are linearly independent. Okay? So that's the next thing we'll do. So here I just repeat the definition of the polynomials. And now we're going to use a couple of properties of these polynomials. So the first property is this one here. If I plug in u sub j into f sub I, I'll end up with 0. So why is that? Well, let's imagine we plug u sub j in here. Then we'll get u sub I in a product with u sub j. And that will give us plus or minus alpha by definition of equiangular line system. This will be plus or minus alpha squared. So this whole thing is alpha squared. Then minus alpha squared times u sub j in a product with itself. And that will give us 1, because u sub j is a unit vector. So we plug this in and we'll get alpha squared minus alpha squared. So we end up with 0. So that's the first property. Second one is if we plug u sub I into f sub I, then we end up with 1 minus alpha squared. So to see that, if we plug in u sub I here, we'll get u sub I in a product u sub I, which gives us 1, since it's a unit vector, and then minus alpha squared times u sub I in a product u sub I, which is again 1. So we'll end up with 1 minus alpha squared, this one here. Okay, now we'll do the linear independence check. So we'll multiply them all by some coefficients. And we want to show that the only way this can be 0, this linear combination of polynomials, the only way this is 0 is if all of my coefficients are 0. So I want to show that this equality implies that each CI is 0. So that's what I'll do now. So we start off with this equality here. This linear combination is 0. And now we'll plug u sub I into it. And what will happen if we plug u sub I into this, then most terms will just go to 0, right? All of these f sub j's where j is not equal to I, they'll just disappear. They'll turn into zeros. And one of them won't, precisely one of them won't. That will be the f sub I term. And that will give us c sub I 1 minus alpha squared. And now we can divide by this 1 minus alpha squared, since alpha is not 1. And we end up with ci is 0. And we can do that for all I. And so therefore we see that these polynomials are indeed linearly independent. And therefore their number is bounded above by the dimension of the space they live in. Okay, and this I think is quite a cool result. So yeah, I hope you enjoy that or interested to look into it further. And this polynomial method can be generalized and used for similar problems. Okay, so we've just proved the absolute bound, and that says the best you can do, the best number of lines in dimension D is D times D plus 1 over 2. Now, we just proved an upper bound, so every time we prove an upper bound, we think to ourselves, is it possible to get equality here? Like, how good is this bound? And so now we can check some dimensions that we know about. So for example, we know about dimension 2, we can get 3 equiangular lines in dimension 2. And so if we plug 2 into here, what do we get? We get 2 times 2 plus 1 is 3, divided by 2 is 3. So the absolute bound says 3 is the best you can do in dimension 2. And we know that we can get 3 lines in dimension 2, and therefore we can attain equality in dimension 2. And that immediately tells us that 3 lines in dimension 2 is the best we can do. So we solve dimension 2 immediately. Now we can look at dimension 3. So we plug this one in. So we're plugging in D is 3 into this. So I'll get 3 times 3 plus 1 is 4, divided by 2 is 6. And we know that we can get 6 equiangular lines in dimension D. And so now we're quite excited. Maybe the absolute bound is the answer to this whole problem. However, it doesn't quite work out. And in fact, we'll see, well, we don't, this is actually an open problem as to where does equality hold for this band. So what we know is that we can attain equality in this band when D is 2, 3, 7, or 23. So we know that we can attain equality here. We've actually seen 7, so you can plug in 7 here and you'll get 28. And one we haven't seen is dimension 23. So I'll tell you about dimension 23 later on. But as far as we know, these are the only dimensions where equality can be attained here. And it's an open problem to work out if there are any more dimensions. So it's widely believed by the community that these are the only dimensions where equality can be obtained. But still, this is open. So there's some dimensions where they've been ruled out. In fact, many have been ruled out, but there are infinitely many open. So there's a lot of room to make progress on this particular problem. And as I said, we'll see how to construct the 276 lines in dimension 23 later on. Okay, so that's absolute bound, and this is a very important upper bound, and this gives us a quadratic upper bound on number of lines. So this says D squared plus D over 2 is the best we can do. Now we're going to think about lower bounds. So what we've seen, let's go back to the table. We've seen we get a quadratic upper bound, but here I'm defining n of D to be the best possible. So best in terms of size, so the largest possible equiangular line system in a given dimension. So now I want to have a look at lower bounds to understand the nature of this function n of D. So now I'm going to show you about a quadratic lower bound. And to do that, I need to tell you about so-called mutually unbiased bases, MUBs. So here comes the definition. So we start with a bunch of orthonormal bases for R to the D. So we have B1 is a basis for R to the D. So is B2 all the way up to BK. So we have these K bases and they're all orthonormal bases. And now we're going to insist on this very special property. So the extra condition is here. Suppose that for all I not equal to J, and for all vectors V in BI, basis I, and W in basis J, we have that the absolute value of the inner product of those two vectors is constant. So this is our extra condition. And if this holds, then we say that this set of bases is called a set of mutually unbiased bases for R to the D. Okay, so now let's just think about what this means. So what it's saying is that if I take any two vectors from different bases, then there's a constant, I get a constant absolute value of inner product between those two vectors. But imagine I take two vectors inside the same basis, then I should get a zero inner product because they're in the same orthonormal basis. So therefore, the inner product between them should be zero because it's orthonormal. Any pair is orthogonal. And so now I have these two different absolute value of inner products floating around. I have this one, which is constant, and then I also have a zero inner product as possible. So let's have a look at an example. So here we're going to look at R to the 4. And in R to the 4, we can find a set of 3 mutually unbiased bases that look like this. So I've put the vectors as columns of a matrix. So here's my first one. This is a very standard orthonormal basis. You just take all of the standard basis vectors. So that's one. This is an orthonormal basis. If I take the inner product between any two, I'll get 0. Here's another orthonormal basis. So this time I have a bunch of plus or minus 1s, and I have to normalize by 1/2 to make sure they're all unit vectors. And you can check if you take the inner product between any two vectors in this basis, you'll get 0. And similarly over here, take the inner product between any two vectors, you'll get 0. So these are 3 orthonormal bases. And now they have this very special condition that if I take the inner product of any vector over here with any vector over here or over here, I'll get a constant absolute value inner product. So let's do that. So it's a bit boring because these are just going to give us a particular entry of these vectors. So this will give me 1 times 1/2 plus 0 times everything else. So I see that I'll get a 1/2 with this vector with any of these vectors. But if I take this one, so this second vector here, I'll sometimes get a 1, I'll sometimes get a 1/2 and I'll sometimes get a -1/2, right? So I'll get plus or minus 1/2. Absolute value though is always constant. And this also holds between these two as well. So I need this to hold between any pair of bases. So I can also take any vector in here and any vector in here. I take the inner product and I still get absolute value 1/2. Okay, so this is MUBs or mutually unbiased bases. These are another very interesting object in their own right. And there's a open problem about how many MUBs can you get in 6 dimensions. Okay, there's a question in the chat, and it says, the vector I consider is the row vector or the column vector. Here I'm considering column vectors. Okay, but I'm not sure that it matters. It might still work actually with row vectors, but I am considering in this example column vectors. So these are MUBs, mutually unbiased bases. And now we can use these to construct equiangular line systems. So now I'm going to show you how we can use mutually unbiased bases to get equiangular line systems. And this corresponds to a construction originally given by Duquesne in the year 2000. And he uses MUBs to get this lower bound. He says that n of d, or the maximum cardinality of an equiangular line system, is at least m squared over d, for d equal to 3m over 2 minus 1, and m is a power of 4. So this is an infinite construction, and it gives us the lower bound for particular dimensions. And together with Munomasa, Colin, and Salerci, we kind of extended this construction to get this general lower bound. So using this idea, pushing it a tiny bit, we can get this lower bound for n of d as this quadratic expression. So the important thing to note here is this is also a quadratic expression in d. This is 32d squared plus 328d plus 296 over 1089. So these numbers are not very important. Don't need to care about these numbers, these coefficients really. Important thing is that it has order d squared. So I want to briefly show you how you can do this, how we can turn mutually unbiased bases into equiangular lines. So let's see, how do we do this? Well, I'll show you by giving you the idea of how to prove this theorem. So this is the main tool, and it says that for any power of 4, so m is again power of 4, we can construct this number of lines, m times m over 2 plus 1, equiangular lines in this dimension 3m over 2 plus 1, or this number of lines, so it's just the same number minus 1, equiangular lines in one fewer dimension, or m times j for this number of dimensions. So it's just a way to construct equiangular lines given mutually unbiased spaces. So it's not really important to remember these numbers in general. I'll give you the idea, the general idea how this works. So here comes the idea. So I'm just going to illustrate the proof using one example. So I'm going to start off with m is 4. And if m is 4, then using work of Cantor, we know there's m over 2 plus 1 mutually unbiased bases in R to the m. So this actually works for any power of 4. That's why the power of 4 thing is quite important here. So in particular, it works when m is 4, but if m is 4 to the t, we still have this many mutually unbiased bases in R to the m. And so when m is 4, then m over 2 plus 1 is 3. And so these are our 3 mutually unbiased bases here. This is what I showed you on the previous slide. So again, you can check this is a set of mutually unbiased bases. And now we're going to turn this into vectors that span equiangular lines. So what we do is we take the vectors of our orthonormal basis and we put them as columns for a matrix. But the problem here is that the inner product between any pair of vectors at the moment is not a constant. The absolute value is not a constant. Because sometimes we get 0, or sometimes we get 2. So if I take this inner product here and here, I get 2. If I take this one and this one, I get 0. So this is not yet an equiangular line system. So now we're going to add on some extra rows just to make it work. So this is the idea. We add on a bunch of extra rows like this, and we normalize it just to make them unit vectors. So this normalizing factor, don't really care about that. Not really a big deal. It's just to make them unit vectors. The important thing is this little extra trick we did where we just added on 3 extra rows. And we did this to make sure that now the inner product between, the absolute value of the inner product between any pair of vectors should now be constant. So let's try to check that. So if I do this one, this first vector here, inner product with this second vector, what do I get? Well, I'll get 2 times 0 plus 0 times 2 plus 0 plus 0, and then square root 2 multiplied by square root 2. So that will give me 2. So I'm just ignoring this factor here. It doesn't really matter. So if I take the inner product between these two, I'll get 2, right? Because I'm just hitting these square root 2's together. So any pair of vectors in this subset of 4 vectors, the inner product will be equal to 2. And the same thing is true for this block here of 4 vectors and this block here of 4 vectors. So if I take the inner product between any pair here, then this part will give me a 0 inner product, and then this will give me square root 2 times square root 2, which is 2 again. So the idea is I'm just adding on some vectors and making sure that the inner product between any pair of vectors that's originally inside an orthonormal basis has the inner product that I want, just by putting in some extra entries. So that's the idea. So now this set of 12 lines is an equiangular set of lines. The absolute value of inner product between any two of these column vectors is constant. Is just equal to a third. So that's how it works. And now we want to check the dimensions that we get. So after we did this, we added 3 extra rows. So we started off in dimension 4, but then we added 3. So we ended up in dimension 7. So that gives us 12 equiangular lines in dimension 7, because we had to add on 3 extra rows. But now we can use some extra tricks so that when we delete vectors, the dimension should drop. So here I'm living in dimension 7. Now if I throw away one of my vectors, it looks like it still lives in dimension 7, right? So it's still dimension 7 because I have 1, 2, 3, 4, 5, 6, 7. 7 entries. But all of these vectors are now orthogonal to something. So can you see a vector that's orthogonal to all of these vectors? So it's not so easy to spot this. So I'll show you that my claim is every vector here is orthogonal to this vector. So let's check that. So this vector has a root 2 at the top, and then these 3 have a 0 there, and it has 2 minus 1s at the bottom, where these 3 vectors all have 0s there. So if I take the inner product between this vector and any of these 3 vectors, I get 0. Because I'll get 0 times root 2, 0 times minus 1, plus 0 times minus 1. So that's okay. Now if I do it over here, in these next 4 vectors, then each one has a 1 in the first entry, and each one has a square root 2 in the 6th entry. So now if I take the inner product between any of these vectors and this vector, I'll get 1 times root 2 minus 1 times root 2 minus 1 times 0. So that gives me root 2 minus root 2. Again, I get 0. And the idea is similar here. So here I'll also have 1 times root 2, and then minus 1 times 0, that's minus 1 times root 2. So again, I get 0 in a product. And so that allows me to argue that these 11 lines, so here I have 1, 2, 3, plus 8 lines, even though it looks like they live in dimension 7, because they're all orthogonal to some vector, I can project them into a smaller space. So I can reduce the dimension by 1. And I can apply this trick one more time. So I can throw away these 3 vectors. So if I throw away these 3, I just have these 8 vectors left. Then I know they're all orthogonal to this vector. But you can see there's another vector that all of these vectors are orthogonal to. Can you see the vector? So the trick is to look for common entries, and we see that the 1, 2, 3, 4, the 5th entry is always 0. So I can actually throw away this entry if I like, or I can argue that it's orthogonal to this vector here that just has a 1 in the 5th entry. And so that allows us to reduce the dimension by 1 again. And so actually these 8 lines here, they live in 5 dimensions. And this is actually the same as what Duquesne got with his construction. So our construction is just like a slight generalization of Duquesne's, and this allows us to get this lower band. So we can summarize what we've seen so far. We've seen a quadratic upper band for n of d, and we've seen a quadratic lower band, and so therefore we know asymptotically that the behavior of this function is quadratic. So we have approximately d squared lines in dimension d. That's what we know so far. And so now the next thing to do, now we know the approximate behavior of this function, the next thing to do is try to get more concrete results about what is the exact value for particular dimensions. So continue this trend. So first, I just wanted to show you that the behavior is quadratic in D. So now we're going to push this a bit further. And now we're going to get some matrices involved. So the next thing I want to tell you about is Seidel matrices. And this is where you start off with an equiangular line system and you turn it into a relatively nice matrix. So this is what I want to do next. So here I introduce the Seidel matrix, and we start off with equiangular lines, again, given by x. So it's just a bunch of lines, say L1 up to Ln. And we assume the common angle is bigger than 0. So common angle 0, again, is very boring. That's just an orthonormal basis. So you can always just take, so let's just go back to a concrete example. I can always just take some set of vectors like this, right? Just the standard basis. That will give me d lines in dimension d, common angle 0. Not very interesting at all. And so we avoid this case because it causes us some problems if we allow this to come into our definition for Seidel matrix. So we assume common angle is positive. Now for each line, we take a unit spanning vector like normal. So we can write each of our lines as the span of a particular unit vector. And if we do that, then we know the inner product between any pair of unit vectors is plus or minus alpha. This is just the absolute value of this is equal to alpha. And so since it's real, the inner product itself must be plus or minus alpha. Okay, so we have a bunch of vectors. Now we can take the Gram matrix of our set of vectors, and that's just the matrix of inner products of our vectors. So the ij entry, the Gram matrix, is just the inner product of vector I with vector j. So that's our Gram matrix. And the Gram matrix looks quite nice because all of our vectors are unit vectors. So we get ones on the diagonal. And on the off diagonal, we'll get the inner product between any pair of distinct unit vectors, which we know should be plus or minus alpha because it's an equiangular line system. So our Gram matrix looks like this. And now we can clean this up a bit more. So you might already think that this matrix looks quite nice, but the alpha might not be a nice number. So let's hide alpha away. So what we do next is we delete the diagonal by subtracting the identity matrix. So here I do M minus identity matrix, put zeros on the diagonal, and then I can divide by alpha. So if I divide by alpha, my plus or minus alphas will just become plus or minus ones. And so I end up with what we call the Seidel matrix, and that's a symmetric matrix, zeros on the diagonal, and plus or minus ones on the off diagonal. Okay, and we can reverse this process. So we started off here with an equiangular line system, X, and we ended up with this matrix, zeros on the diagonal, plus or minus ones on the off diagonal. We can run this in reverse. We can start off with a Seidel matrix, just zeros on the diagonal, plus or minus ones on the off diagonal, turn it into a Gram matrix, and then decompose that and find these vectors. So this is a forward and backwards relation. So now instead of looking at equiangular line systems, we can instead study these matrices known as Seidel matrices. Okay, now we want to understand properties of our equiangular lines system using a matrix. So that's the next thing we'll try to understand. And the key thing that we're going to focus on for Seidel matrices is the smallest eigenvalue. So let's see why that happens. So we'll go back to our unit spanning vectors u1 up to un. So we start off with our n vectors. Then we can put these vectors into a matrix, just column vectors like this. So I just put my u1 over here, u2 next to it, up to un. And let's assume that these vectors live in, the smallest dimension they live in is r to the d. So this has rank d. Now we can form the matrix of inner products by just taking the transpose of this matrix multiplied by itself. So if you think about it, that should give you the Gram matrix, because the first entry would be this one transpose multiplied by itself. So just imagine that here I'm just having column vectors, ui's, and here I have, sorry, the transpose will give me row vectors for my ui, and B has column vectors for ui. And so when I multiply this thing together, I'm multiplying my row vector with my column vector, and that's precisely giving me inner products of these vectors. So that's how you can see this. Now, it's a Gram matrix, and it has this form, and so the smallest eigenvalue of this is 0. So I'm not sure if you've seen this before, but this is a basic property of Gram matrices, that they're positive semi-definite, and so therefore their smallest eigenvalue should be 0. And then you can use rank nullity to work out that the multiplicity of the 0 eigenvalue is just n minus d. This is the nullity of the matrix. And now when we do our shift to get a Seidel matrix, so we minus I divide by alpha, what happens to the smallest eigenvalue is it gets subtracted by 1, so we'll get 0 minus 1 and then divide by alpha. And so the smallest eigenvalue of the Seidel matrix will be minus 1 over alpha with multiplicity the same, n minus d. Okay? And so this means that we can extract all the information about our corresponding equiangular line system just by looking at the smallest eigenvalue of a Seidel matrix. So what the smallest eigenvalue itself will tell us the common angle, alpha, and the multiplicity will tell us how many, well, the multiplicity is n minus d, and we know n because this is an n by n matrix. And so you just take the size of the matrix minus this multiplicity, and that gives you the dimension that it lives in. So we can read off all the important information about our equiangular line system just by looking at the smallest eigenvalue of the Seidel matrix and its multiplicity. Okay, so when you're given a Seidel matrix and you want to understand properties of the equiangular line system, you want to find the smallest eigenvalue. Okay, so now we can study Seidel matrices to study equiangular lines. So now let's have a look at some properties of Seidel matrices. Okay, so let's start off with a Seidel matrix and call it S, and assume it has order n. So it's an n by n matrix. The first thing we can observe is that the trace of the Seidel matrix is 0. So why is that? Well, the trace is just the sum of the diagonal entries. But we know each of the diagonal entries is equal to 0. So the trace is just 0 plus 0 n times. And so we see that all Seidel matrices will have trace equal to 0. Next nice property is if we square the Seidel matrix and then take the trace, what happens then? So if we square the matrix S, then if we go back to the picture, we're just going to be doing plus or minus 1 squared plus or minus squared. For each of these off-diagonal entries, when you square this matrix, I'll just be summing the squares of the entries in some row. So the first one will be 0 squared plus 1 squared plus 1 squared and so on. So my diagonal entry of s squared will be n minus 1. So I can actually attempt to write that if we look at s squared, then it will look like this. We'll have n minus 1 on the diagonal. And so now when I take the trace, I'm just summing up a bunch of n minus 1s n times. So I know the trace of s squared will be n times n minus 1. Okay, now we can map these trace observations to the eigenvalues. So here I'm going to assume that my Zydo matrix has eigenvalues lambda I. So lambda 0 is the smallest one up to lambda n minus 1. So it has n eigenvalues. They're all real because it's a real symmetric matrix. And the trace is telling me the sum of the diagonal entries, but it's also telling me the sum of these eigenvalues. So the trace, this is equal to the trace of S. The trace of S is also equal to the sum of the eigenvalues of S. And similarly, the sum of the squares of the eigenvalues is equal to trace of S squared. So we immediately get some information about all of the eigenvalues of a Zydo matrix. Okay, good. So now I can tell you about another bound, a slightly more precise bound for the size of an equiangular line system. This is called the relative bound. So it's a bit stronger than the absolute bound because we also assume something about the common angle. So we have that X is an equiangular line system with n lines in d dimensions with common angle alpha. This is the common angle. Common angle. And the claim is if we assume that d is at most 1 over the common angle squared, then we can get this bound here. So n is at most d times 1 minus alpha squared divided by 1 minus d times alpha squared. And there's a nice extra conclusion to this theorem that if you get equality in this bound, then you know that the Zydo matrix has precisely 2 distinct eigenvalues. And we can see a couple of examples of this going back to our 2-dimensional and 3-dimensional examples. So here we have three equiangular lines in dimension 2. This is the corresponding Zydo matrix. And this configuration corresponds to equality in the relative bound. And so we expect the Zydo matrix to have 2 distinct eigenvalues, and the eigenvalues of this one is just -2 and 1. So for this one, remember the angle here was a half. So for this one, we had angle is equal to a half. And so you can check, you can plug all these numbers in. So we have n is 3, d is 2, alpha is a half. And so this should give you 3. So this configuration gives you equality in the relative bound. And the conclusion says that the eigenvalues of this matrix should just consist of just 2 distinct values. In this case, -2 and 1. Slightly more interesting case is dimension 3. So here the angle was 1 over square root 5. And this is something, again, you can check just by looking at the spectrum of the Seidel matrix. So here we have 6 equiangular lines in dimension 3. This is the corresponding Seidel matrix. So this is a 6x6 matrix. And again, we get equality in the relative bound. And so therefore we should have the spectrum of this matrix consists of just 2 values. So we just get 2 distinct eigenvalues. In this case, minus square root 5 and square root 5. And another thing you can do is check that all these trace identities hold for these 2 matrices. And here you can also check that the smallest eigenvalue is -1 over alpha. Okay, so that's quite nice to see that we have another bound, and it tells us something about something even stronger about the eigenvalues of the Seidel matrix. So now I want to show you how to prove this. So I just clear my drawings, and let's see how the proof of this thing works. And I always say the proof of this is essentially just the Cauchy-Schwarz inequality. So I don't know if you've seen the Cauchy-Schwarz inequality. If you haven't, then good thing to look it up. And if you have seen it, then I want to emphasize that it's a really, really useful inequality. So it should be highlighted how useful Cauchy-Schwarz is. Comes up all the time. So let's see how it works for us for this theorem. So we want to establish this upper bound, n is at most d times 1 minus alpha squared divided by 1 minus d times alpha squared. And so to prove this, we're going to get a Seidel matrix involved. So we're going to let S be the Seidel matrix for this system of n equiangular lines in R to the d. And we know that the smallest eigenvalue of our Seidel matrix must be -1 over alpha, and the multiplicity should be n minus d. So we know that n minus d of our eigenvalues for S are equal to -1 over alpha. Now we can let lambda 1 up to lambda d be the other eigenvalues. So the other eigenvalues not equal to lambda 0. And then Cauchy-Schwarz gives us the following inequality. So Cauchy-Schwarz says that the square of the sum of these d eigenvalues is at most d times this sum of eigenvalues squared. Why is that? And so if you want to see where this comes from, you can just take the all ones vector, inner product with the vector of lambdas, lambda 1, lambda 2, up to lambda d. So I take the inner product of these two things, squared. Cauchy-Schwarz says that's at most the square of the inner square of the length of the all ones vector. This is all ones vector. Let's call this 1, and let's call this bold lambda. Then this is at most 1 inner product with itself times lambda transpose lambda. So apologies for my rough writing with a mouse, but this is what the Cauchy-Schwarz gives you. And so you see that on the I forgot the squared on the left-hand side. So this should be, oh yeah, I have got squared. Okay, good. So if we look at this inner product, we'll get 1 times lambda 1 plus 1 times lambda 2 and so on. And then the whole thing squared. That gives you the left-hand side. And this one, inner product of 1 with itself is just 1 plus 1 d times, so d. And then inner product of lambda with itself is just lambda 1 squared plus lambda 2 squared and so on. So that's the Cauchy-Schwarz inequality helping us out. So I repeat it here. This is what we established. And now we can use the trace observations. So here we use the trace of S is 0. So the sum of the eigenvalues should give us 0. So that here we have n minus d times lambda 0 plus the rest of my eigenvalues should be 0. And the sum of the square should be n times n minus 1. So we get these two equalities, and now we can rearrange them. So here I can use this inequality to get an expression for the sum I goes from 1 to d of lambda I. So this, if I put this one on the other side, so I cancel over here and I put cancel here and I put minus n minus d lambda, and then I can plug that into here, and that will give me this expression. And similarly, I can put this on the other side. So this will be minus lambda 0 squared n minus d. And then I can put that over here. And then this Cauchy-Schwarz inequality becomes this inequality here. I should underline this part. And then we can simplify this. So if we simplify this inequality, we end up with this part, n times lambda 0 squared minus d is at most d times lambda 0 squared minus 1. And this could be rearranged to this, sorry, this could be rearranged to the relative bound on the previous slide. And the last thing to do is worry about equality. So in the case of equality, we'll have equality in the Cauchy-Schwarz inequality. And so this is a consequence, again, of the Cauchy-Schwarz inequality. Okay, I see a question in the chat. Thanks for your question. It says why we multiply with d in the inequality. Yeah. So this is this d here, I suppose. Why do we multiply that? That's because that's the inner product of the all ones vector with itself. So I wrote a small explanation where on the right hand side, this over here is just the all ones vector inner product with itself multiplied by the lambda vector inner product with itself. And this one here is just the all ones vector inner product with the lambda vector squared. So the d is coming from here. So this is equal to d. Because there are d entries here. So the all ones vector is equal to just the vector of ones, d times. Okay. Thanks for the question. So I should probably clear some of this stuff. Okay, so for the case of equality, we end up with equality in Cauchy-Schwarz, and that tells us that all of these lambda I should be equal to each other. So we see that lambda 1 equals lambda 2 all the way up to lambda d. This is just consequence of equality in Cauchy-Schwarz. And now we can use trace of S as 0, and that will tell us what our lambda i's should be equal to. So you use this equality, and then you end up with just two values. You have your lambda 0, and you have your lambda 1, which is equal to lambda 2 up to lambda d. And these are your two eigenvalues. So these are explicitly worked out values, but importantly, there are just two values here. Okay, and so that tells us the relative bound. The relative bound, the summary is it's pretty much just Cauchy-Schwarz, just applied in the right way. So we've seen relative bound, and now I want to tell you about a really special construction of equiangular lines known as the Witt design. So this is the Witt design here. And this corresponds to an equiangular line system in 23 dimensions, consisting of 276 lines. So I want to give you a quick construction of this, of the corresponding Seidel matrix. So that's what I'm going to do here. So it's kind of a miraculous construction. So you start with a polynomial. So we start with this polynomial here, P, and it has degree 11. So it's x to the 11 plus x to the 9 plus some other stuff up to plus 1. And all the coefficients are in F2. This is a field of 2 elements, just 0 and 1. So all the coefficients are just 0 and 1. And we're working over F2, finite field, with just 2 elements. Now we're going to form this set capital P, and that's going to be all powers of this polynomial reduced modulo x to the 23 minus 1. So it's a bit of a strange set to consider, but there's some good explanation of this if you go into parts of coding theory, but I won't go into this stuff. That maybe some of the other lecturers will go into more detail here. This is a particular design. But today I'm going to just give you a bare bones description. So we have the set P of all powers of P, and then B for blocks, by the way, will be a subset of P that consists of those polynomials having precisely 7 non-zero coefficients. Okay? So we take this strange set of powers of P, reduce modulo x to the 23 minus 1, and then I take the subset of that where I only consider those polynomials that have 7 non-zero coefficients. Okay. So the first point is that if you work out B, so you can plug this into your computer, work out what B is, you'll see that the cardinality is 253. So just to give you an explicit example of something that lives in B, this is something that lives in B. So if we take P, the polynomial P of x to the 39, reduce it modulo x to the 23 minus 1, we end up with this polynomial here, x to the 22 plus x to the 21, all the way down to x. And this is in B because there are just 7 non-zero coefficients, 1, 2, 3, 4, 5, 6, 7. And so that belongs to B. Also, P to the 1, by the way, so P itself has just 7 non-zero coefficients, 1, 2, 3, 4, 5, 6, 7. Okay, so we collect all of these 253 polynomials using this construction, and now we turn this into a 0, 1 matrix. So I'm going to take n to be my 0, 1 matrix, and the rows are the coefficient vectors for each of these polynomials in B. So we know there's 253 polynomials, so we're going to end up with 253 rows, and it's a coefficient vector of a degree 22 polynomial, so we need to have 23 columns. So we have x to the 22 all the way down to x to the 0. So in total, we need 23, 22 plus 1. So to give you an example of what this matrix looked like, I can give you 2 of the rows. So the first row corresponds to P. So here we have 1, 1, and that's because we have non-zero coefficient here, 1 for the 0 position, so that's this one, and then 1 for the x to the 1 monomial, and so we get a 1 here. Then there's no x squared term, so we have 0 times x squared, so I have this 0 here, and then 0 times x cubed, so I get this 0, 0 times x to the 4, this 0, but then I have 1 times x to the 5, so I get a 1 here. I also have x to the 6, x to the 7. There's no x to the 8, so I have a 0. There's x to the 9. There's no x to the 10. There's x to 11. And then there's nothing higher than x to the 11. So all of these are 0. So this is x to the 12, x to the 13, all the way up to x to the 22 here. So that's how the first row looks. This is just the coefficient vector for this polynomial P. And the second row, that's going to correspond to this one here, P x to the 39. So this one it has a 0 here, which means there's no constant term. And then there's a 1 here because we have an x. Then 0, 0 because we don't have x squared, x cubed. There's a 1 here because we have x to the 4, and hopefully you get the idea. And then we have 2 1s here because we have x to the 21 and x to the 22. Okay, and then you just fill in this matrix with all 253 coefficient vectors. So you probably don't want to do it by hand. You probably do it by computer. Okay, so we get this matrix N like that. And now we observe that N has a nice property that if we do N times N transpose, we look at the ij entry, we'll get 7 if we're on the diagonal, or 3 or 1 if we're not on the diagonal. So there's only 2 different off-diagonal entries and 1 diagonal entry. So the 7 on the diagonal is quite easy to see. That's just because you have 7 non-zeros on each row, right? So 1, 2, 3, 4, 5, 6, 7. Those ones are going to hit each other to give a 7 on the diagonal when you do N transpose. And then 3 or 1, that just means if we take any 2 rows, they agree in 1 or 3 positions. So here, the inner product between these 2 rows would be 1 because they just agree here. They have a common 1 here and then no other common ones. Okay, so it has this nice property. And now we can turn this into a Seidel matrix. So this is how we turn this matrix N transpose into a Seidel matrix, which we call W for the bit design. We have a 2x2 block matrix. We put J minus I on the first diagonal. So here J is the all ones. J is the all ones matrix. And so on, all ones matrix. And I is the identity matrix. So we have 0 on the diagonal and then 1s everywhere else. And then here we do J minus 2 times N transpose. So J is all 1s. If we minus 2 times N transpose, then since N has just 0s and 1s, if we do a 1 minus 2, we'll get minus 1. 1 minus 0 gives us 1. So this is just plus or minus 1 here. Similarly, plus or minus 1s down here. And then we have this expression in the bottom diagonal. That's N times N transpose minus 5 times identity minus 2 times J. So first of all, the diagonal of this is 7, but then we minus 5. So now the diagonal is 2. Then we minus 2 from here. So now the diagonal is 0. On the off diagonal, it's either 3 or 1. So on the off diagonal, we get 3 or 1, and then minus 2. So if it's 3 minus 2, we get 1. If it's 1 minus 2, we get minus 1. So this whole bottom diagonal is also a Seidel matrix. Okay, so this whole thing is a Seidel matrix, and it turns out, and you can check this in the literature, that W just has 2 distinct eigenvalues, minus 5 with multiplicity 253, and 55 with multiplicity 23. So now if we work out what's the corresponding equiangular line system, we just need to read off these numbers. So we see the angle should be 1 over 5. That's because the smallest eigenvalue. So alpha equals 1 over 5. And this thing is n minus d. And we know n is the size of this matrix, which is 23 plus 253. So that's 276. And so therefore, d must be equal to 23. Yeah, actually, in the case of 2 eigenvalues, you can read off d as the other eigenvalue. Okay, so this is quite an amazing yeah, construction. So there's a comment in the chat. It's a good question. So it's going back to this polynomial. Is there any specific reason why it's this polynomial? It seems to come out of nowhere. Yeah, I agree, actually. So I don't know much about where this polynomial comes from, but it's related to a construction of something called a Golay code. And with discussions with others, I know they tell me that it's quite understood where this polynomial comes from, but I personally don't know. So I can't answer your question, but it's an interesting question and a good thing to look into. Okay, so we have this miraculous construction of 276 lines in dimension 23, and we can actually use that to get other good constructions of equiangular line systems. There's another comment in the chat. How do we get to know that the cardinality of B is 253? So this is something you can do by computing it. I don't know if there's a general formula that will tell you how many blocks you get for a particular polynomial. So again, this is outside of my area of knowledge. Okay, so now we're going to see how we can use this 276 lines to get other large constructions. And so here I just summarize all these different constructions one can obtain, starting with 276 lines in dimension 23. And this actually corresponds to quite a lot of the large constructions. So I've given the table below. So here's the table of the latest values for n of d. And by looking for principal submatrices of this matrix, you can find the following construction. So you can get 176 lines in dimension 22, which corresponds to the best possible value. 126 in dimension 22, again, corresponding to the best possible. Then it's also known you can construct 90 equiangular lines by looking inside the Witt design, but we don't know that's the best possible. So it's not known that 90 is the best. So far, it could be possible to get 94, not sure. For 19, also the best possible is currently 72, but we don't know if that can be improved. And also recently, the lower bound for 18 went up to 56, but we know this is not the best. So we can actually do better than a construction found inside the Witt design, but there's some asterisks to point out here. So I'll say a bit more about that later on. And 48 equiangular lines in dimension 17 is also inside the Witt design, and that is the best possible. Okay, so now I want to comment on this 56 and dimension 18. So because of all these other good constructions from the Witt design, it's a good idea to look inside the Witt design. And so far, the best known construction in dimension 18 coming from the Witt design corresponds to 56 equiangular lines. However, we found a totally independent construction. So I'll show you how to get 57 lines. So you can get 57 equiangular lines in dimension 18 in the following quite simple way. You simply take these integer vectors. So what we did was we looked for vectors whose entries are all integers. So it's just, you have 18 coordinates, all of them integers, and you look for them having this length, having length 10. So the squared length 10. Inner product with any vector with itself has length 10, and the inner product between any two distinct vectors is plus or minus 2. So we looked for that, and we managed to find 57 such vectors that correspond to equiangular lines in dimension 18. And here is one of the systems we found. So I've just put as columns all of these vectors. You can see they're all integers. There's a plus or a minus to mean plus or minus 1. And then there's also some 2's floating around. So these are 57 columns. Each one spans a line, and those are equiangular lines in dimension 18. And you can compute the Seidel matrix using this transformation here. So this matrix is B. You take B transpose B. The diagonal is going to be 10 because they have squared length 10, minus 10 times identity. And instead of plus or minus 1s on the diagonal, we have plus or minus 2. So we divide by 2, and we end up with a Zeidel matrix. And this is the characteristic polynomial of this Zeidel matrix. So here you see the smallest eigenvalue is -5, and the multiplicity is 39. And the rest, there's 18 other eigenvalues. So the corresponding equiangular lines lives in 18 dimensions, and there's 57 of them. So now we know that this is not inside, we know that this configuration doesn't live inside these 72, but we don't know how to show that an equivalent set of lines doesn't live in the Witt design itself. So it could be the case that you can still get 57 lines inside the Witt design. We just don't know at the moment. So it's an open problem whether you can get 57 or more lines from the Witt design. So this is not fully understood. And it'll be quite interesting if you can show that the Witt design, for some reason, is not the best thing to look for in dimension 18. Okay, so we've seen Witt design, we've seen some constructions. Now I want to talk about even more constructions and how that connects to some other areas of combinatorics. So I'm thinking maybe this is a good time to take a break. What do you think?
Yeah.
Yeah, I think I've been speaking for a while now. How long have I been speaking so far?
I think it's more than an hour already.
Okay.
So maybe how long do you want to take a break? 10 minutes or?
Yeah, we
10
can
minutes
take,
enough? All right.
Yeah, 10 minutes is fine, yeah.
Okay, so participants, we will start again at Indonesian time in 3 o'clock. So 10 minutes from now. Okay, thank you very much.
Fakultas Matematika dan Ilmu Pengetahuan Alam Institut Teknologi Bandung atau disingkat FMIPA ITB merupakan fakultas yang menyediakan program studi berakreditasi unggul dan terbaik di Indonesia bagi mereka yang ingin mendalami pengetahuan di bidang kimia, fisika, astronomi, dan matematika. FMIPA ITB merupakan yang tertua dan terdepan di Indonesia di bidang matematika dan ilmu pengetahuan alam dengan reputasi yang sudah diakui secara nasional dan internasional. Sebanyak 20 program studi yang ditawarkan terakreditasi A atau unggul oleh Badan Akreditasi Nasional Perguruan Tinggi. Dan keempat program studi di tingkat sarjana mendapatkan akreditasi bergengsi secara internasional. Setiap tahun, FMIPA ITB mendidik lebih dari 2.300 siswa, baik di tingkat sarjana, S2 maupun S3. Dalam memberikan pengajaran berkualitas, dosen-dosen FMIPA ITB didukung oleh 16 kelompok keilmuan yang aktif melakukan berbagai penelitian. Kelompok keilmuan astronomi bertujuan untuk mengembangkan ilmu astronomi, astrofisika, ilmu luar angkasa, dan ilmu lain yang berhubungan dengan astronomi. 6 kelompok keilmuan fisika aktif melakukan riset tentang bumi dan sistem kompleksnya, tentang material-material yang ada di alam dan pemanfaatannya, tentang material magnet dan fotonik serta pengembangannya, dan banyak lagi lainnya. Di bidang kimia, 4 kelompok keilmuan secara produktif mencari temuan-temuan baru untuk pengembangan, penerapan, dan penyebarluasan ilmu kimia, serta penyelesaian berbagai masalah yang berkaitan dengan kimia di masyarakat. Begitu juga dengan 5 kelompok keilmuan matematika, di mana para dosen di dalamnya mendukung proses pembelajaran matematika, serta pengembangan dan penerapan matematika di dunia modern saat ini melalui penelitian mereka. Proses pembelajaran dan kegiatan riset di FMIPA ITB didukung oleh fasilitas-fasilitas mumpuni yang dimiliki oleh fakultas. Observatorium Boscha merupakan observatorium modern tertua di Indonesia dan Asia Tenggara, sehingga memiliki peran yang sangat penting di dunia dalam pengamatan dan eksplorasi benda-benda angkasa. Laboratorium Fisika Terpadu dan Laboratorium Kimia Terpadu di FMIPA ITB memungkinkan para peneliti dari kelompok keilmuan yang berbeda-beda untuk dapat mengakses berbagai peralatan penelitian di satu lokasi saja, yaitu di masing-masing laboratorium terpadu tersebut. FMIPA ITB memiliki deretan kontribusi nyata dalam memajukan ilmu pengetahuan yang dinikmati oleh mahasiswa, masyarakat, dan juga industri. Bagi mahasiswa, komitmen FMIPA ITB dalam mendukung mahasiswa memaksimalkan kompetensi ternyatakan melalui upaya untuk secara rutin mengirimkan mahasiswa ke ajang kompetisi internasional yang sangat bergengsi seperti Olimpiade Matematika.
FMIPA ITB memfasilitasi mahasiswa FMIPA untuk berkompetisi pada tingkat nasional maupun internasional. Fasilitas yang disediakan berupa pembinaan dan akomodasi yang meliputi biaya maupun tempat pelaksanaan. Pada tahun 2021, FMIPA mengirimkan 5 mahasiswa pada kompetisi matematika internasional IMC 2021 dan berhasil mendapatkan 2 emas, 2 perak, dan 1 honorable mention.
Bagi masyarakat, lewat kelompok-kelompok keilmuan, dosen dan staf FMIPA ITB giat menjalankan pengabdian masyarakat yang sangat membanggakan fakultas.
Observatorium Boscha bersama dengan program studi dan kelompok keahlian astronomi di FMIPA ITB mengupayakan agar konsep-konsep dasar sains yang berkenaan dengan astronomi itu dapat menjadi bagian dari hidup masyarakat yang terintegrasi. Observatorium Boscha dengan dukungan FMIPA bekerja sama dengan banyak pihak, bisa NGO, bisa industri, bisa korporasi, jadi ada banyak yang bekerja sama mendukung program pendidikan astronomi yang menyediakan sumber belajar yang tidak ada batasnya. Karena peran Observatorium Boscha dan astronomi di ITB di bawah FMIPA ini ada banyak sekali yang berhubungan langsung dengan masyarakat. Umpamanya saja pengamatan bulan baru, hilal, bagaimana hari-hari penting itu ditentukan. Banyak sekali kontribusi dari Observatorium Boscha.
Kami telah banyak kerjasama dengan berbagai instansi pemerintah pusat dan daerah, pihak swasta dan industri di dalam maupun luar negeri untuk memajukan pendidikan, penelitian, dan pengabdian masyarakat. Kita telah juga membuka layanan penggunaan alat lab bagi masyarakat luas, diantaranya SEM, Microcity, NMR, alat praktikum pengajaran, dan HPC yang ada di gedung BSCA, dan juga peralatan lain yang tersebar di gedung Prodi dan juga Observatorium Boscha. Dengan peralatan ini, kami telah memberikan pelayanan dalam bidang pendidikan, penelitian, dan industri. Kerjasama dalam bidang penyelenggaraan beasiswa pasca sarjana juga telah kita lakukan, diantaranya penyelenggaraan pendidikan S2 pengajaran bagi guru, di Departemen Agama dan juga Provinsi Bangka Belitung dan akan menyusul beberapa Pemda lainnya. S2 dalam bidang aktuaria untuk staf BPJS Ketenagakerjaan dan pendidikan S2 Master by Research dan Doktor by Research di lingkungan organisasi penelitian BRIN. Pendidikan S3 bagi staf Kementerian Perdagangan dan lainnya. Kami juga sangat concern dalam upaya membantu meningkatkan kualitas pendidikan menengah dan dasar yang diramu dalam program peningkatan kompetensi guru dan siswa, memberikan pelatihan bagi para laboran atau teknisi, penyiapan bahan ajar, modul praktikum, dan lainnya. Kami siap bekerja sama.
Sementara kiprah FMIPA ITB bagi industri hadir dalam bentuk kinerja riset dan inovasinya.
Pada saat awal pandemi COVID-19, kami kemudian diminta oleh BPPT BRIN untuk mengembangkan alat uji cepat deteksi antibodi COVID-19. Nah, kami bersama-sama peneliti di FMIPA, kemudian SCTH, dan juga mitra industri kami, PT Pakar Biomedika Indonesia, didukung oleh BPPT BRIN dan juga tentu saja FMIPA, kami mengembangkan alat uji cepat untuk deteksi antibodi COVID-19. Alat yang dihasilkan dinamakan e-COVID-19, saat ini sudah tervalidasi dari FK Unpad dan kami sedang melakukan pengajuan izin edar.
Dalam hal pendidikan, khususnya untuk peningkatan SDM dari industri itu, untuk saat ini kita berfokus pada peningkatan SDM dari industri keuangan dan juga peningkatan SDM di industri alat-alat berat ya, khususnya untuk pengolahan data besar. Bekerja sama dengan BPJS Tenaga Kerja, di sini kami sudah bisa memberikan kontribusi bagi dunia industri dengan meluluskan sebanyak 5 staf dari BPJS Tenaga Kerjaan di dalam bidang asuransi. Demikian juga di industri alat-alat berat, di sini kami juga memberikan pelatihan bagi SDM PT Komatsu Indonesia dalam rangka mempersiapkan mereka untuk memberikan pelatihan di manajemen bisnis ya, untuk mendapatkan Deming Prize.
FMIPA ITB secara berkesinambungan aktif berkontribusi dalam pengembangan dan penerapan matematika serta ilmu pengetahuan alam untuk kesejahteraan masyarakat Indonesia. Bergabunglah dengan kami dan kembangkan potensi Anda secara maksimal.
Okay, Dr. Gary, are you already with us?
Yep, I'm ready.
All right. Yeah, okay. Let's start again the session. You have another 45 minutes before we start the question and answer session.
Okay, perfect.
Yeah.
Okay, welcome back, everyone. So now I want to connect Zydo matrices with graphs. So I'll do that on this slide. So you start off with a Zydo matrix. As we know, it has zeros on the diagonal, plus or minus ones on the off diagonal. And we can think of this as a graph adjacency matrix, where the minus ones are corresponding to edges of a graph, and the ones are corresponding to non-edges of a graph. And more concretely, we can write the graph adjacency matrix A.
Sorry, sir, you haven't shared your screen yet.
Oh, I forgot to do that.
Yeah.
Okay. Can you see my screen?
Yes, perfect.
Sorry, I forgot my screen's not shared. So we can write the graph adjacency matrix like this. So A equals J minus I minus S. Again, J is the all ones matrix, I is identity matrix, and then minus S, which is this one here. If we do this, then this will give us a graph adjacency matrix just having zeros and ones. So in this example, we'll get this matrix here, which corresponds to this graph. Okay, and you can go back and forward actually between graphs and Zydo matrices. So if you want to write down this Zydo matrix with respect to this graph, you just put minus ones where there are edges and ones where there are no edges, and zeros on the diagram. Okay, so we can get graphs. Now I want to tell you about a particular family of graphs that are quite important when it comes to these really good equiangular line systems. So I'm going to define this family of graph using this graph here. So here's a graph, right? It has a few nice properties. First property it has is that each vertex has the same number of neighbors. So I can illustrate that with this symbol. Vertex goes to k, meaning that every vertex has k neighbors. So in this example, let's take this vertex here. How many neighbors does it have? Well, I can highlight all of its neighbors. So it has 1, 2, 3, 4, 5, 6 neighbors. And then I go to another vertex and look at all of its neighbors. I see 1, 2, 3, 4, 5, 6. And I can keep doing this. So I can check that each vertex has 1, 2, 3, 4, 5, 6 neighbors. And I have a k in this case is 6. So it's regular. It's a regular graph with degree k. It also has another further property that any pair of adjacent matrices has the same number of common neighbors. So I illustrate that with this picture here. So 2 adjacent matrices and then lambda common neighbors. So I can take any pair of adjacent vertices like these two here, and then I look at their common neighbors. So both of these vertices are adjacent to this one, and this one. So I see they have 3 common neighbors. I can take another pair of adjacent vertices, these 2 red ones, and they again have 3 common neighbors. And I can keep doing this. So these 2 again have 3 common neighbors. And in fact, any pair of adjacent vertices has precisely 3 common neighbors. Okay. There's one further property. So it's regular with degree 6. Every pair of adjacent vertices has 3 common neighbors. And we also have that any pair of non-adjacent vertices has the same number of common neighbors. So here we can take these 2 non-adjacent vertices. Number of common neighbors is 1, 2, 3, 4. Try it with another pair. These 2 red ones. Number of common neighbors is 1, 2, 3, 4. And you can keep going. These 2 have also 4 common neighbors. And in fact, any pair of non-adjacent vertices has 4 common neighbors. And so this graph is quite special. And we call such a graph strongly regular. So we call it strongly regular if it's regular, every pair of adjacent vertices has the same number of common neighbors, and every pair of non-adjacent vertices has the same number of common neighbors. So we can write down these parameters like this. So we say SRG for strongly regular graph. 10 is for number of vertices, has 10 vertices. 6 is the regularity. 3 is the edge regularity. And 4 is the co-edge regularity, it's mu. Okay, so strongly regular graphs. Before I move on, I just want to talk about comment in the chat. So it says, what if we multiply S with -1? Then I think we still get a matrix. Yeah, that's true. So just going back to this correspondence, if you multiply S by -1, then all the -1s become 1s, all the 1s become -1s, and so the graph you get will be the complement of the graph you got with your original S. So you still get a graph. There's another question, and we always get a regular graph corresponding to S. That's not true. So you might not get a regular graph. This is not a regular graph here. So we'll see more about the graphs we get from Seidel matrices. So I introduced strongly regular graphs using this example. So strongly regular have these three properties: regular, edge regular, and co-edge regular. Now there's a nice correspondence with Seidel matrices. And in fact, this correspondence works for any regular graph. So that's summarized in this lemma here. So if gamma is a simple connected n-vertex k regular graph, so as n vertices, every vertex has k neighbors. And we assume the adjacency matrix has these n eigenvalues. So it's connected, so the largest one has multiplicity 1, and then we have lambda 2 up to lambda n other eigenvalues. Then you can take the corresponding Seidel matrix, J minus I minus 2a, that's a Seidel matrix, and the eigenvalues are easy to write down. You get n minus 1 minus 2k, coming from the first, or the top eigenvalue, and then minus 1 minus 2 lambda I for all the other eigenvalues. So this works for any regular graph. Now, for strongly regular graphs, using these properties that we have, this k, this lambda, and mu, it can be shown that a strongly regular graph will have three distinct eigenvalues. And if you have fewer eigenvalues, it's more likely that the multiplicity of the eigenvalues will be relatively large. And what we want with a good Seidel matrix corresponding to a large construction of equiangular lines is that one of our eigenvalues, the smallest eigenvalue, should have high multiplicity. And so if we want to get it from a graph, we'll want also, if our graph's regular, we want the eigenvalues of the graph to have high multiplicity. And so you can typically do that if you don't have many eigenvalues in your graph. And so here I've got a table of constructions of equiangular lines that correspond to strongly regular graphs. So it means if you have a strongly regular graph, you take the corresponding Seidel matrix, what spectrum do you get? And here I have a bunch of n and d. So number of equiangular lines n, dimension d. Here I have strongly regular graph and the parameters below. So remember we saw the Witt design, 276 lines in dimension 23. That had Seidel spectrum, these two eigenvalues, minus 5 to the 2, 5, 3, 55 to the 23. This actually corresponds to a strongly regular graph on 276 vertices. And the strongly regular graph spectrum looks like this. So we get a 23 here. We get 2 to the 252, and we also get 140. So these two, when we do this transformation, J minus I minus 2a, these two eigenvalues, 140 and 2, they get mapped to minus 5. So these two multiplicities kind of combine to get 253 here for the minus 5. And we have a similar phenomenon happening for other good constructions of equiangular lines. So we have these other strongly regular graphs giving us these large constructions in various dimensions d. Okay, and we'll see why this is not really a coincidence. There is a good reason for this. So this is related to this theorem by Taylor. So Taylor in the 1970s said that if you have a Seidel matrix with just two distinct eigenvalues, then there must exist a corresponding strongly regular graph with one less number of vertices. So this is an n by n cytomatrix with 2 eigenvalues, and this is a strongly regular graph on n-1 vertices. So there's a correspondence between these two things. So if we have such a strongly regular graph, we can construct the cytomatrix. If we have the cytomatrix, we can construct the strongly regular graph. So a basic example of this theorem in action is going back to our icosahedron. So 6 lines in dimension 3. We saw that the cytomatrix has this spectrum here, minus square root 5 and square root 5, both with multiplicity 3. So here we're in this case, we have 2 distinct eigenvalues for our cytomatrix, and it corresponds to a strongly regular graph with these parameters. So here it's a 6 by 6 cytomatrix, and here we have 5 vertices, and then you can work out these parameters R and S just by working out these numbers here. Okay. So to see this in action, again, we'll go back to a picture of our icosahedron. So this is our 6 lines in dimension 3. This is the cytomatrix. And we saw it has these 2 eigenvalues, minus square root 5 and square root 5. Now, to talk about connections with graphs, we have to be a bit careful with what we mean. So in the previous slide, I was talking about you have an adjacency matrix A, and then you go to a cytomatrix by J minus I minus 2 times A. That's one way you can pin down a graph. But when it comes to cytomatrices, they come from spanning vectors of lines. Now, when you have a line, you have 2 options for your spanning vector. You can either go like one way in your line, or you can point the opposite way. There's kind of 2 directions for every line in your system. And that corresponds to something called a switching of the cytomatrix. And so what it means is we can conjugate our cytomatrix with these diagonal plus or minus 1 matrices, and they'll give us the same lines, because all we're doing is we're swapping the direction of our spanning vector. So we're free to do this. And every time we do that, we're going to get a slightly different matrix. The eigenvalues will be the same, but the plus or minus 1 configuration will be slightly different. So this is where we talk about the switching class. And here we're talking about all the different possible graphs. So a switching class is where we get all of the possible adjacency matrices that can correspond to a particular equiangular line system, not a particular cytomatrix. Okay, so to try to make that a bit more clear, I've written out the switching class for this, this configuration of equiangular lines. So the first one, so the first one I've highlighted in red. So this is a pentagon with an isolated vertex. So how do we get that from the cytomatrix? Well, the first row and column, you see we only have non-negative entries. So in the adjacency matrix, we would have zeros everywhere, right? There'd be no edges coming out of this vertex. And so that corresponds to this isolated vertex here. And then for all the other rows, we just have precisely 2 minus 1s. So this submatrix, so if I annotate this, if I look at this submatrix here, sorry, that's not a very good drawing. Submatrix here, you see there's 2 minus 1s in each row. And so the corresponding graph will be a cycle. So we get this 5 cycle and an isolated vertex. However, that's a particular switching of our spanning vectors. So I could switch it by doing this. So when I switch it now, I multiplied all the rows and columns from the first, I multiplied all the entries from the first row and column by -1. And so that's by conjugating by diagonal matrix having -1 as the first entry, all other entries 1. So now, instead of these all being non-edges, I get every possible edge coming out of this first vertex, and that corresponds to this graph here. So I still have the cycle structure, but now my isolated vertex is suddenly adjacent to everything. Okay, and I can keep going. So if I switch the second row and column, then I get this highlighted graph at the bottom. So now I switch again, and my resulting graph looks like this. So you can see my first row has 1, 2, 3, 4, 4 minus ones. So it's either this one or this one, or this one. So one of these three, these will have degree 1, 2, 3, 4. My second row has 2 minus 1, so it's one of these ones here. This one has 4 minus 1, so it's one of these three, and so on. So we get a different kind of graph, but the line system stays exactly the same. And finally, if we keep switching, we'll also get this possibility, this graph. So these 4 graphs, they all correspond to the same equiangular line system. But the most interesting one from Taylor's perspective is the first one, because it corresponds to a strongly regular graph. So this 5 cycle, this is strongly regular. So this 5 cycle is SRG 5, 2, 0, 1. And this was actually the example on the previous slide, the 5, 2, 0, 1. This is the strongly regular graph he's talking about. So Taylor's idea is to switch so that there's one isolated vertex, and he can prove that the remaining graph will be strongly regular. Okay. So now let's compare that with the relative bound that we saw earlier. So the relative bound says that if you have equality, then the corresponding Zydo matrix must have 2 distinct eigenvalues. And Taylor says if your Zydo matrix has 2 eigenvalues, then there must exist a corresponding strongly regular graph. So if we combine these 2 results together, anytime we have equality in the relative bound, there must exist a corresponding strongly regular graph. And so these special strongly regular graphs are equivalent to, in some sense, the best possible equiangular line systems. And so there was a big effort to try to understand these strongly regular graphs. And so by understanding strongly regular graphs, you can construct the corresponding equiangular line systems. And even more amazingly, in my opinion, is there were some researchers just working on the best possible equiangular line systems, and they managed to find new strongly regular graphs based on their constructions. So it flows both ways. So you can get new results for strongly regular graphs by studying equiangular line systems without even caring about strongly regular graphs. So that's a correspondence there, but we'll see later that you can't just restrict yourselves to strongly regular graphs when you want to understand equiangular lines. Okay, so that's it for the introduction. Now, in my remaining time, I'm not sure how far I'll be able to get through, but I want to tell you about some more advanced methods and how we can demonstrate maximality. So the first thing I'm going to start off with is how to identify the right common angle to deal with. So this is attributed to Peter Neumann back in, again, the 70s. And he observed that if there exists n equiangular lines in dimension d, and the number of equiangular lines is more than 2 times the dimension, then 1 over alpha must be an odd integer. So this really simplifies the possible angles that we need to consider. So at the beginning, you might be thinking, okay, the angle could be anything, any number you like. But Peter Neumann says, well, if you want to have more than 2 times d lines, then you're going to have to restrict yourself to odd integers. So suddenly, this continuous looking problem turns into a discrete problem, because we always want to do better than 2 times d. So we pretty much always restrict to 1 over alpha is odd integer. So now we can immediately just say, okay, 1 over alpha is an odd integer. And we can start looking at bounds for a slightly related quantity. So here I'm going to define a slight specialization of n of d, the maximum cardinality of an equiangular line system. I'm just going to restrict to those having a particular common angle. So I define n of 1 over alpha of d to be the largest n such that there exists n equiangular lines in d dimensions having common angle alpha. So using Neumann's results, usually this 1 over alpha is going to be an odd integer. And putting together a bunch of basic results, we can prove the following lemma. So if d is strictly less than some odd number squared, then this n of d is at most the maximum of all of these quantities. So it's this restricted n for various odd, where alpha is 1 over an odd number. Okay, so we can restrict our attention like this. And this is a consequence of the relative bound together with some other relatively straightforward observations. And so now we can actually start to prove some upper bounds. So on this slide, I want to prove that n5 equals 10. Okay, so I'm going to keep this lemma up just to keep it in our minds. So I want to prove that n of 5 is equal to 10. So how can I do that? Well, first of all, I know that I can get 10 lines in dimension 5. How do I know that? Well, it was shown earlier. So I summarized it in this table here. We can get 10 lines in dimension 5 using this graph here. Does anyone know what this graph is called? Strongly regular graph, 10 vertices, and every vertex has 3 neighbors. Peterson graph. Yeah, exactly. Good. So someone said Peterson graph. Exactly. This is just the Peterson graph. So Peterson graph is also showing up here. So we know that we can get 10 lines in dimension 5. So we just need to show that we can't get 11 equiangular lines. So we'll do this using contradiction. So we'll assume that there exists 11 equiangular lines in dimension 5. And Neumann says, since 11 is more than 2 times 5, the angle, 1 over the angle, must be an odd number. Now, we can apply this lemma here because 5 is less than 2 times m plus 1 for all natural numbers m. So 3 squared, 5 squared, and so on. 5 is always less than that. So we can directly apply this one. And in general, n of 2m plus 1, the relative band gives us its at most this number here. So this is just plugging in the relative band where my 1 over alpha is 2m plus 1. I get this expression. But I can simplify this expression. So if I manipulate this a bit, I have an m squared plus m on the numerator. I do some basic arithmetic. I can turn this into 5 plus 5 over m squared plus m minus 1. And then I can realize that my m for any natural number, this is going to be strictly less than 11. So this will be, my upper bound will be less than 11, but I assume there's 11 equiangular lines in dimension 5, and so I get a contradiction. So I assume there's 11, and the bound tells me I can't have 11. So I get a contradiction. So I know that I can't have 11 lines, and so therefore n of 5 is equal to 10. And this is really the basic idea for all of these maximality proofs. You kind of just show that you can't have one more than the best known construction. Okay, so because of Neumann's observation, it tells us that we should study this specialized number. So either n of 3, n of 5, n sub any odd number. And this was done to some extent all the way back in the 70s. So Lemons and Seidel, in their seminal paper, they showed that if you restrict to the angle being 1/3, then the best you can do is 28 lines for these dimensions. And when your dimension goes at least 15, you get some rubbish band. You get just 2 times d minus 1. So you get something just linear in d. So we know that this is rubbish because we have a quadratic lower band. So Lemons and Seidel essentially say, if you want to find a good construction with angle 1/3, you probably want to look at dimension at most 15. Otherwise, if d is at least 15, then you're not going to get good constructions. And recently, this was done for 1 the common angle is 5. So Sao, Paulin, Lin, and Yi recently showed the same thing for 1/alpha is 5. They showed that it's 276. So this is corresponding to Witt design, all the way up to dimension 185, and then it becomes linear. Then you just get this floor of 3/2 d minus 1 for dimensions more than 185. So these results allow us to focus on particular angles and help us restrict our effort this way. And recently, the asymptotics were figured out. So there's a nice pattern here. So you have 2 here, then 3/2, and then the next one will be 4/3. And in general, if you have n of 2m plus 1d, then if d is large enough for any fixed m, you can show that this is equal to the floor m plus 1 over m times d minus 1. So you get this kind of band. So we know the asymptotics, but what we want to know is the critical range of when you should stop considering particular odd numbers for your 1/alpha. So we can see how to apply these results by working out n of 13. So to show that n of 13 is 28, we know that we can get 28 lines in dimension 7, and that also fits in dimension 13. So we just want to show we can't get 29 lines. And so here we have a similar idea, but now we can rule out n of 3. So there's a small annoying point in this lemma that we need d to be less than 2m plus 1. And if your d is too large, it means that your m also gets restricted to be large. So you need another way to deal with the small m, and that's what these theorems allow us to do. So these theorems can help us figure out what happens for various small m. So the next open case would be n7. But here, 13 is not less than 9, right? So 13 is bigger than 9. So for 1/alpha is 3, we can't just use the relative band. So what we can do instead is use Lemons and Seidel's result, that the best you can do is 28, all the way up to dimension 50. So we can use this, and it says that if there are 29 equiangular lines, 1/alpha can't be 3, right? Because otherwise the best we can do is 28. And so now we can use that 13 is at most 2m plus 1 for all other m. So the next one would be 5 squared, which is 25. So 13 is less than 25. And so we can again apply the relative bound, and this time it gives us 26. And so again, we get a similar contradiction, and we can deduce that n of 13 is 28. Okay, good. So that's some basic demonstration of how we can establish part of our table. So now I'm going to show you the table again. So you can use the techniques we've seen so far to get all the way up to dimension 13. However, it doesn't work for dimension 14. Dimension 14 is quite tricky because this doesn't work. You don't get 26 here. You actually end up with 31. So you don't quite get the right upper bound. So 14 is separated here. And you can get 36, but you can't get 16, 17, all the way up to 20. So after this point, I think I don't have that much time, but I'll at least tell you a bit about how we can make a bit of progress. In this table, I've also given 1 over alpha. So we saw that 1 over alpha is 2 root 5 for these small constructions. And for these other constructions, it can be 3 and then 5. So this is like illustrating these theorems here. So 3 is a good number for your 1 over alpha all the way up to dimension 13. But then it starts being ineffective, and then 5 takes over, and then at some point 7 will take over, and so on. So we have this kind of pattern where different odd numbers are going to be the right thing to choose when we choose our common angle. Okay, we also saw that the best constructions can sometimes correspond to strongly regular graphs, and this means that their Seidel matrix will have 2 or 3 distinct eigenvalues. So let's have a look. Here I'm indicating by 2, the best construction has 2 distinct eigenvalues. So for all these constructions, there exists a construction that has just 2 eigenvalues. But notice there are no constructions here that have 2 eigenvalues. So the study of strongly regular graph is not going to help to here. So this is for 2 eigenvalues, and hopefully this will tell you that you can't just limit yourself to looking at strongly regular graphs. You have to do a bit more. And now I've indicated 3 where there exists a construction where the Seidel matrix has 3 distinct eigenvalues. And so you can see here, there's a construction with 3 eigenvalues all the way down to dimension 4 that gives you 6 lines. There's a construction in dimension 14 for 28 lines using 3 eigenvalues, and so on for these ones. And then 4, this construction in dimension 20 to give you 90 lines, it has 4 distinct eigenvalues. But notice this one is missing, right? The 57. So 57, the construction I showed you, has 7 distinct eigenvalues. Using this restricted number of eigenvalues might give you the impression that 57 is not the best possible, or maybe it's the case that some of the best constructions have a lot of distinct eigenvalues. So this is also unclear. What we showed with Colin, Munamasa, and Slushy in 2016 is that if you want to get close to the relative bound, so not quite equal, but as close as you can without being equal, then that restricts the spectrum of the corresponding Seidel matrices. So we saw earlier that if you want to get equality in the relative bound, the corresponding Seidel matrix has just 2 distinct eigenvalues. But sometimes equality is not possible. Sometimes the relative bound is not an integer. So instead, you can look at the floor of the relative bound. And if you want to get equal to the floor, then we found that in many cases, the spectrum is completely determined. So what it means is that if there exists 30 equiangular lines in dimension 14, the corresponding Seidel matrix must have this spectrum. So we know that the smallest eigenvalue should be -5 and the multiplicity should be 16. But we don't know a priori what the other eigenvalue should be. So we can push it a bit further and we can work out the entire spectrum. And so this means if we want to find 30 equiangular lines in dimension 14, we must restrict our attention to Seidel matrices having this spectrum. And we can do similar things for other configurations. And we can write down the corresponding spectrum for a Seidel matrix having number of lines equal to the floor of the relative bound. So I've done that on this slide for these dimensions. But notice that in the table, the upper bounds are not equal to the numbers given, right? So here I have 30, but actually the answer is 28. So somehow we ruled these out. So I want to give you some idea how we ruled these things out. So firstly, I colored this one blue because there do exist 36 lines in dimension 15. This one is quite easy to show it doesn't exist because it has an even eigenvalue of high multiplicity. So it had 10, it should have an eigenvalue 10 with multiplicity 17. But we can show that even eigenvalues cannot have multiplicity greater than 1. So I'll try to make sure I get to at least that slide before the end to show you how that works. And we can also kill off the rest with various techniques. So I won't go into all the techniques, but we can kind of one by one go and show non-existence of Seidel matrices having these corresponding spectra. Okay, so in order to do this, we can employ techniques like the relative band, push them a bit further to tell us a bit more about the spectrum. So on this slide, I have that S is a Seidel matrix, and phi dx is a polynomial of degree d, integer polynomial. And so what we can show, I won't explain this, but using some more advanced techniques, we can show that the characteristic polynomial of a Seidel matrix that corresponds to 29 equiangular lines in dimension 14, not only do we know the smallest eigenvalue, but we can work out 4 other eigenvalues. And then there's 10 unknown eigenvalues. And we can do similar things for 41 lines in dimension 16, 49 lines in dimension 17. And these are just 3 examples. So we can do this for lots of different cases, but just ones of interest are dimension 14, 16, 17, because that's where we're focusing on our upper bounds. So we can work out some of the other eigenvalues, and then it remains to work out these factors, which have degree 10, 13, and 13. So the way we can make progress on this is by identifying some very interesting pattern for the determinants of a Seidel matrix. So on this slide, I'm collecting together a bit of history for the determinant of a Seidel matrix of a certain order. So here, I attribute the first observation back to Harmers in 2012, who observed that the determinant of a Seidel matrix is congruent to n minus 1 modulo 2. So it means that if you know the order of a Seidel matrix, you can figure out what its determinant is, if it's odd or even, essentially. And in 2016, we pushed this a bit further to modulo 8. So in fact, similar thing is true for modulo 8. 1 minus n is the determinant modulo 8. Very useful congruence. And then we pushed it much further to not just talk about determinants, but talk about all of the coefficients of the characteristic polynomial. So we can determine not just the determinant, the constant coefficient, but all of the congruence classes for every coefficient of the characteristic polynomial of a Seidel matrix. And we have very strong restrictions on these things. And this is one of the ways we manage to make progress. So if we change n to be odd, we get slightly weaker results. And this one sums up a lot of observations we can make from this. So I've summarized it in this corollary. So if S is a Seidel matrix order n, then if we reduce the characteristic polynomial, so this characteristic polynomial is I'm using chi for this, so this is just determinant xi minus s, so just the characteristic polynomial. And so here we find that the characteristic polynomial of the Seidel matrix is congruent to this one or this one, depending on whether n is odd or even. And this is just using that we get the characteristic polynomial of j minus I, the complete graph, essentially. All ones matrix minus identity matrix. So we can summarize it like this. So it's either congruent to this one or this one. So if we take a look at what this is telling us, imagine that your characteristic polynomial has an even eigenvalue, so an even root. Then you would get an x minus k factor where k is even. If you reduce that modulo 2, that would just become an x factor. because the k is even, so it disappears to 0. And so immediately we can see that if you have an even eigenvalue, the multiplicity is at most 1, because here you don't get no even eigenvalues possible. Here, there's just 1. So we can immediately observe that even integer eigenvalue has multiplicity at most 1. And furthermore, if n is even, you can't have any eigenvalues. Any even eigenvalues. There's no x factor here. And another one, you can keep going with these observations. So you also can't have square root 2 as an eigenvalue of any Seidel matrix, right? Because the minimal polynomial would be x squared minus 2, and that would be congruent to x squared modulo 2. So that will give you an x squared factor, but there's clearly no x squared factor no matter what. So you can't have this. So there's a lot of very interesting consequences from quite a basic looking results. And so this is one way we managed to make progress. So I think I have to, can I just ask how much time I have left?
Sure, about 5 minutes left.
5 minutes, okay. So I need to skip a few slides. So I wonder what to skip here. Maybe I'll say something about this slide, since it gives you a relatively easy way to see that determinants should have a high power of 2 dividing them. So if you start off with a Seidel matrix, you can write it like this: j minus I minus 2 times A. And you can absorb this minus I into the argument x. So the characteristic polynomial of j minus I minus 2a is equal to the characteristic polynomial of j minus 2a, where instead of x, I have x plus 1. And so if you think instead of Seidel matrices, but of these slightly shifted matrices, it's quite easy to see that they have an intimate connection with the number 2 when it comes to determinants. So for example, if I look at determinant of j minus 2 times an adjacency matrix, then it looks like this. It's like a Seidel matrix, but you have 1s on the diagonal because you're not minusing I. So you have 1s on the diagonal and then plus or minus 1s on the off diagonal. And so to work out the determinants, you can do some elementary row operations, and that preserves the determinant. So here what I can do is subtract the first row from all the other rows. So if I do that, the first row stays the same, but then these 1s become 0s, these minus 1s become minus 2s, and so on. So if I subtract the first row from all other rows, all the entries below the first row are going to be equal to 0 or minus 2. So now when I take the determinants, I can take out factors of 2 of each of these rows below the first row. So this gives me a factor of 2. Second row, third row gives me a factor of 2. And so I immediately see that 2 to the n minus 1 divides the determinant of this j minus 2a. And so that's a basic way of seeing that if you work modulo power of 2, you're going to get quite strong restrictions on characteristic polynomials of Seidel matrices. So I'll just skip through this extra bit of detail. In the interest of having open problems to talk about, we get these bounds on the number of congruence classes for Seidel matrices modulo powers of 2. So we see these bounds here, and we conjecture that equality is always possible. So here's a couple of conjectures that you can think about. So the first one says if k is at least 3, then if you make your n large enough and even, then there's going to be equal to 2 to the k minus 2 choose 2 congruence classes for the characteristic polynomial of a Seidel matrix modulo a power of 2. And we have a similar one for the odd case. So if it's odd, then we have a similar one that if you make n large enough and odd, there's precisely this number of congruence classes for characteristic polynomials of Seidel matrices modulo power of 2. Okay, so this is open conjecture. I think it's quite an interesting thing to work on. I'll skip over this one. yeah, I have quite a few slides that I may have to skip. So let me just summarize what I wanted to say. So I was just going to give you more details on particular restrictions we can make for what possible characteristic polynomials should correspond to particular systems of equiangular lines in given dimensions. So unfortunately, I have to skip over all of this super interesting stuff. But I have given some online talks that you can look up on YouTube that contain similar details. So I think I'll stop there. Thanks a lot for your attention, and feel free to ask questions if you have any.
All right. Thank you very much, Dr. Gary. Let's give a round of applause for our speaker. Yeah, unfortunately, the time is limited. So even if it's really interesting and motivating lectures we had today for the very first day of International Virtual Course today. And let us now open a quick question and answer session. For those who wants to ask Dr. Gary directly, you could just raise your virtual hand using the available Zoom features. Perhaps 1 or 2 questions. Is there any questions from anybody? Is everyone still here? May I see your face? Can you open the video, please? Yeah. Is there, or if anyone has comments on the lecture today? Okay, no. Perhaps because some of the questions in the chat box are already answered during the lectures. So maybe there are no more questions. Let me just wait for another minute. Okay, nobody wants to ask questions. Yeah. Well, then perhaps let's just finish this session today. But before we end our Zoom session, let us have a second photo session with Dr. Gary. Maybe Fitri can help me to take the picture. Is Fitri still here? Fitri or come? Yeah. Hello, Fitri?
I can help you on taking the picture.
Okay, yeah, thank you, Kamal. All right, so maybe how many slides, Kamal? 4?
Wait a minute. I think before we're proceeding to the photo session, may Professor Gary to unshare the screen first, because we really want to see the gallery session. Okay. It should be 5 slides.
All right.
It requires a lot of time. So yeah, Ma'am Intan, you can guide us on taking a picture, and I will help you on taking the picture.
Okay. Everyone, can you open your camera, please? Yeah. Okay. Now let's have the first photo. 1, 2, 3. Smile. Okay. Now the second slide. 1, 2, 3. All right. The third one. 1, 2, 3. All right. The fourth. 1, 2, 3. Now the last one. 1, 2, 3. Smile. Okay.
Thank you.
Yeah. I think this is the end of today's International Virtual Course 2022 Combinatorics Perspective. And I hope you guys learned a lot today from what the speaker gave us. And so I will see you again tomorrow on the next class with Professor Akihiro Munemasa. Take care and goodbye.